Section 4.4 is titled The Fundamental Theorem of Calculus. And anytime somebody starts putting fundamental in front of a theorem, it means it's pretty important, right?
Oh, yeah.
There is a fundamental theorem of algebra. There's a fundamental principle of counting. Anytime they put that fundamental word in there, it's really important. Pay attention.
What's the fundamental principle of counting?
Fundamental principle of counting says that if you have something like 5 ways of doing one task and 6 ways of doing another task, and you want to do both tasks, then it would be 5 times 6 ways of doing any combination of those tasks. So, yeah, that's what it is. It's a good one. You guys use it all the time. You just don't even think about it. Okay, we're doing calculus, though. So the fundamental theorem of calculus says the following. If f is continuous on AB, and capital F is any antiderivative of f, then the integral from a to b of f of x dx is capital F of b minus capital F of a.
Is the capital F the antiderivative?
The capital F is any antiderivative, yeah. Okay, so jot that down and let me tell you what this is actually saying to you. Okay, in your last section, the one we just finished, 4.4, the only way we had to do antiderivative with the area under the curve stuff, and the only way we had to do the area under the curve integrals was geometric formulas, right? That was one way. And then the other one was when they gave us little specific, very specific pieces, we could break them apart in a very specific way, and then we could use that information. Okay, that's it. That's all we had. But we had this notation that sort of beckoned back to 4.1, and it said, but you've got this sort of script S thing and these antiderivatives, and it's kind of a derivative in reverse. How is it related? Well, this is how it's related. What this is telling you is you can take the antiderivative, and then you can evaluate it at the limits of integration. What's even better is there's no more plus C's.
Yes.
Okay, so I'm going to show you an example of how this works. You guys are going to work through it with me. The first thing we do is we take the antiderivative, so like gateway style stuff, right? So what is the antiderivative of negative 3x? Yeah, okay, so there's various ways of writing it, but I think everybody's saying some version of this. We increase the exponent by 1 to x squared, and we divide by the new exponent. So we have negative 3x squared over 2, or negative 3 halves x squared. That's the first piece. What do we get for the plus 4?
4x.
4x. Fantastic.
So do we put all of that
Okay,
in the
so I'm going to show you first why the plus c's don't matter on this one. So we're going to put them in, and I'm going to show you why they don't matter. So we're going to put plus c just like we would have done before, okay? This is the only one we're going to do it on, I promise. The next thing we're going to do is we're going to draw a vertical bar at the back.
Okay.
The vertical bar is going to have our limits of integration written there. So 5 at the top, 2 at the bottom.
Okay.
All right, so our fundamental theorem of calculus over here says take the antiderivative. That's what these capital F's here are.
Okay.
And then it says to evaluate it at the limits of integration.
Okay.
So we're going to plug the 5 in first. So we have negative 3 times 5 squared over 2 plus 4 times 5 plus c. And all of that is going to subtract the next piece. So then you have negative 3 times 2 squared over 2 plus 4 times 2 plus c. And we're going to address what Garrett just noticed about the c's. What did you notice, Garrett? Right. This one is a c, this one has a c, and there's a subtraction sign here. Do you guys see it?
Yeah.
Plus c minus c. Every time it does that. That's the reason you don't need the plus c's. They add to 0 every time. So if you forget and put it on there, it's not going to hurt anything. It's just not a necessary step. The rest of this we're going to use your calculator and simplify. And go ahead and do this one in your calculator now, and then I'm going to show you a couple of calculator tricks so you can see how you can do this and confirm that you have the right answer and so forth. Okay, so just first go ahead and put this one in, and then we'll do some cool calculator stuff. Okay, did anybody get an answer yet on that one? What'd you get?
Negative 39.
Negative 39 over 2. Or if you write it as a decimal, which is okay too, what would you have? Negative 19.5. And decimals are fine as long as they terminate. If they're repeating decimals, that's not cool. Don't write me a repeating decimal down. You guys are in calculus, okay? We just don't write that way in true mathematics courses, okay? All right, so this is the answer, but I want to show you 2 different ways you can do that. Actually, I have 3 different ways you can do that with your calculator to save yourself a little bit of time. You guys ready for that?
Oh, yeah.
Okay, the first thing I want you to do is I want you to take the antiderivative that you just found and put it into y1. We'll do it from the antiderivative approach first. So that means the piece that we got where we said negative 3x squared over 2 plus 4x. Okay, so first one here, exit the screen. I want you to hit vars, y-vars, function, y1, and put a parenthesis, 5, minus vars, y-vars, function, y1, and put a parenthesis 2. And that should look just like the notation here, f of b minus f of a. So in terms of notation, it really, I switched my screen, you guys can't even see my screen right now. It really looks like what we're doing.
Wait, so we omit the C whenever you put in the y?
Yeah, you don't need the plus c. Okay, if you hit enter, it'll tell you negative 19.5. Now, it'll tell you negative 19.5 as long as you put in the antiderivative. If you accidentally just put in the original function, it's not going to give you that answer. Okay, did everybody's give them negative 19.5 when they tried that? Okay, nobody's did anything funky. Still trying. I'm going to show you another option on how to do this, but I want to make sure everybody gets this one first.
I got negative 51. So is it true?
Okay, anybody else not get what you were expecting or what I was telling you should be expecting? We're all good? Cool. Okay, so this is actually relying on the fact that you found the antiderivative correctly, correct? So what if you made a mistake finding the antiderivative?
You'll know.
Well, you wouldn't necessarily know. You'd know using WebAssign. You might know if you used the back of the book, but you wouldn't know if you were in like a testing environment, correct? You would just think that you got the pieces there right, and that would be great, but what if you actually made the mistake on the antiderivative? So go ahead and hit y equals, and I want you to put the original function in now. Okay? Original function, negative 3x plus 4.
Into Y1.
Into y1. Yeah, and my calculator is going to look different than somebody else's, so I'm going to have to show you what another version of this looks like in a minute. Do you guys remember when we did inderiv on the calculator? Okay, there's a very similar one for function integration. Okay, so I want you to hit math, and I want you to arrow down until it says FNINT. It's option number 9. FNINT. Where's my screen? You can't see it. There it is, number 9 there. Select it. Now, about half of you have this showed up. So raise your hand if yours looks like this. Okay, those of you whose looks like this, I want to show you your steps. And then for those whose doesn't look like this, that was terrible English, I'm going to use somebody else's calculator to show you. Okay, so for those of you who have this on your screen right now, the next thing you're going to do is you're going to tell it y1. So you hit vars, y-vars, function, y1.
I didn't know what a calculator could do this stuff.
What's going
I
on?
know, same.
Well, you paid $200, you should do it.
Yeah, here's the other version. I'll show you guys how to do that in a
Wow,
minute. Okay,
that's easy. I like that.
y1. Does everybody have y1 who has this version? Okay, comma x, because you're telling it I have the variable x in my problem. What's wrong, Bryson? Okay, comma the lower limit, which is 2, and the upper limit, comma the upper limit, which is, 5. Close your parenthesis. And then you hit enter. See that? Negative 19.5. All right, Fallon, do you have yours? Okay, if yours looks like this, okay, so Fallon's got hers entered in. Oops, your screen is so bright. Hang on.
Do you want to use
Oh my word, it's because you got that glowy background. Okay, let's try Bryson.
Oh my god.
Hey, that's weird. Hey, I can't see.
Oh, my word, what in the
I
world?
think it's just so bright.
Too bright.
There
Okay,
it is.
well, it's high enough now, I'll see it. Okay, so right back in your regular screen, again, you're doing math 9, and yours looks like this. So whose looks like this? Okay, yes, Bryson's does because I've got his. All right, this is really cool because it looks just like what's on your paper, right?
Yes.
So you're going to put a 2 down here, you're going to put a 5 up here. You can type the equation in if you want to,
Yeah.
but longer equations become more cumbersome, which is why I always put them in y1. And so we can go vars, y vars, like that.
Okay.
And then you have to put the x at the end. You have all the same pieces of information as my calculator. And you hit enter and it gives you negative 19.5.
Why does it want you to put the x? Like, is there another thing that would make?
Yeah, if you have, when you get further in calculus, Calc 3, we do antiderivatives with more than one variable. That's fine. Yeah. Okay, but you guys are ready for like the coolest thing yet, right? Okay, everybody has this in their calculator for y equals now. Does everybody still have this in y equals?
Yeah.
Okay, I want you to put a standard window, just zoom 6. Okay, just plain old zoom 6.
It's a line.
Now, the reason, of course, you're getting negative areas, because if we're going from what were our numbers 2 to 5, do you notice all the areas down here? That's why we're getting negative area, by the way. So we're getting from 2 to 5, and it's creating this triangle down here.
Yes.
You guys with me? Okay, so here's what I want you to do. All right, this is really cool. I mean, like, you guys are going to love this. Are you ready?
Yes.
Okay, I want you to hit second trace. Second trace is a menu called calculate. Is everybody on the calculate menu?
Oh, that was.
I'm following.
Okay, do you see number 7? Option 7? What's it say?
I don't know.
The integral with the
Yeah, it looks like the notation we've been writing down. So select number 7. On the bottom of your screen, it should say lower limit, does it? What's our lower limit? 2. Type in 2, hit enter. What is our upper limit? 5. Type in 5 and hit enter.
What? That's pretty cool.
It is cool, right?
That's pretty cool.
So this is why this calculator costs $100.
There you go. $100 calculator because it shades in your graph. Now, there is one catch to this, okay?
Okay.
You have to be in the window that shows from 2 to 5. That's why I told you to do your standard window to start with, because I knew that it would go out to 10, you know, from negative 10 to 10. So like, let's say, for instance, we were doing this integral and we were going from 15 to 20. If I tried that on the screen, I wouldn't see anything and it wouldn't calculate anything either. So your screen actually has to go between the x values that you're trying to go between. That's the only catch. Okay, so no matter if you have WebAssign or the back of the book or a neighbor or whatever, you should be able to check all these answers, right?
Okay.
So you do all the work long style, out by hand and so forth, and you plug your numbers in either with the calculator or by hand or whatever. You should be able to check it using the original function in the calculator in one of these two fashions. Are y'all with me? Okay, so we're going to set the calculator aside for a moment. We're going to go back to the by hand part of calculating these, okay? To the Stone Age? No, it's not the Stone Age. Your calculator is a fabulous tool for verifying answers. That's what it is for. I will tell you what, you do have to be smarter than the calculator to use it appropriately. And you guys know that's true, right? I'm sure you've had plenty of opportunity where you thought your calculator did something and it turns out the calculator just, it was a user operator kind of thing, error, right?
One time,
Yeah.
no.
Operator
but
error.
Every other time, yes.
Okay. Trig. All right. We are doing antiderivatives, correct? So what is the antiderivative of 1? X. What is the antiderivative of sine of x? Oh, good. Negative cosine of x. You guys even got the negative in there. You're going to draw your line on the right, pi at the top, 0 at the bottom. What's next? Okay, well, first we're going to write it down. Pi minus the cosine of pi, especially with trig, all right? So all of this piece minus, and then 0 minus the cosine of 0. This one is not a good example to enter into your calculator because it will approximate that pi at the beginning, won't it? So it's not so good. If you're unfamiliar, uncomfortable, or you don't like trig and your unit circle stuff, first of all, that makes me sad. But second of all, your calculator can be used pretty well on this particular one. What is the cosine of pi? Negative 1.
Pi plus.
So this would be pi plus 1.
Minus.
And then we've got a minus here and a minus here to give me a plus again. What's the cosine of 0?
0.
Nope,
1.
1.
Actually,
So this is ending up being pi plus 1, which gives me pi plus 2. And if you approximate the pi plus 2 and tell me that this is 5.17, I'm probably going to melt a little bit inside. I'm going to cry just a little bitty
I
tear.
thought you meant like your heart would be pleased.
No, my heart would not be pleased. So please do not approximate things, all right? Please do not.
Approximate and optimization. Yeah.
Yes, because those are application problems that we have to give an answer in an application sense at the end. It's a very true statement. They still would probably give you a funny stare. Yeah, they probably would.
Is there a way we can like make it pi itself? Pi, like itself?
Say what?
We pay 200 for this. Is there a way for like pi and pi alone?
Not that I know of. Your calculators do have limitations, right? They don't put things in radical form when you're done, or irrational pies. But you know what? If you want to make a lot of money and create a calculator that will do that, I suspect that that would be something people would pay for. So, just thought. All right, what is this one called? The
Man.
second fundamental theorem of calculus.
I thought we were done.
Are we gonna get to
I
memorize?
hate fundamental physics. I hate
Yes.
fundamental-
You are going to remember and memorize either. I will actually ask you for either the second fundamental theorem of calculus or the first one. The reason it says part 2 is because this is a hangover from an old book. So you can mark out the part 2 on your notes. Do your notes say part 2?
No.
Okay. Mine is already marked out then.
Do both of them on the
No, actually, you probably would get all the points taken off because it means you won't know which is which. Still no bonus. So funny. But it's a nice try. All right. If f is continuous on AB and capital F of x is the antiderivative from a to x of f of t dt, then the derivative, that's d dx, that means derivative of the integral is the original function. Okay, what does this say? Well, it says if you take the antiderivative and then you take the derivative, you go back to where you started.
Yes.
It's like rocket science, right?
Yes.
If you multiply by 5 and then you divide by 5, you get back what you started.
At least it makes sense.
Rocket up to the.
Yeah, so there is one catch to that, and I'll show you when we're working in it at the catch.
Oh, no.
The catch comes into play with chain rules.
Bless you.
Do you guys remember chain rules?
Yeah.
I know you do. The catch comes in with chain rules. So I'm going to show you on the first example where the catch comes in, okay? So this will address the why in the world does it have an f of t dt. Well, notice all of this is hinged upon this top limit just being the variable x. Do you see that? What do you notice on the example that we're going to do, though? It says sine of x. What? What is right? What? Okay.
Plug it in.
So let me show you how it works. We know that the idea is we're taking the antiderivative and then we're taking the derivative. So what we're going to do is we're going to actually do the problem out long style, and then we're going to use the fundamental theorem so I can show you where the connection is, okay? So this is not a good example of what I expect you to do on every problem, but I want to show you that it really works. So the first thing we're going to do is we're going to do an example where we're going to take capital F of x. What is the antiderivative? So what is the antiderivative of t? Well, t is our variable, so it actually wouldn't be. Yeah, it would be t squared over 2. Yeah, that's a good question, though, because notice now we have dt at the end, and that's what tells us that it's a variable. And then plus what? 2t. We don't need the plus c because we're still doing definite integrals with limits on top and bottom.
Okay.
We're going to evaluate this at sine of x on the top and at 0 on the bottom. So I'm going to get sine squared of x over 2, right? Plus 2 sine of x. And very technically, I then get minus 0 squared over 2 plus 2 times 0. It's all 0 at the second part. Okay? So what I have then is sine, I'll put the 1/2 in front, 1/2 sine squared of x plus 2 sine of x. And what we just calculated, what we found is f, capital F of x. right? Well, what we're going to do next then is we're going to take the derivative of that. So we're going to find capital F prime of x. All right, so what happens when I have sine squared? There's a chain rule, right? It's sine squared. The squaring is the chain rule, the sine is the inside function, the squaring is the outside function. So the outside function, I take the 2 down to the front, right? So I have 1/2 2 sine of x. And then I need the derivative of sine of x because the sine of x is the inside function. That would be cosine of x. Plus 2. What's the derivative of sine x? Cosine of x.
Okay, so what did we just do?
Well, we took the derivative of what we just found.
Okay.
We took an antiderivative, plugged in the sine x and the 0, and now we're taking the derivative. Okay? So notice what happens. Of course, the 1/2 and the 2's cancel. And I have sine x cosine x plus 2 cosine of x. And I'm going to factor out the cosine of x so that I can show you what really happened. This is sine x plus 2 times cosine x. How did the original problem start out? Well, it started out with t plus 2, and t was sine, correct?
Yeah.
So if I plugged in sine of x for t, I would have gotten sine x plus 2. Agreed?
Yeah.
So where in the world did this cosine x come from? It's the chain rule. It's the dt part. It came from the derivative of the inside, and that's what this is referring to. If you just have x up here, its derivative is 1 and nothing shows up. But if you have another function, like sine x, its derivative is going to be part of the process too. So let's do the process directly like it would have been done if we weren't trying to sort of show that this is what was going to happen. Okay, does everybody have this piece written down?
Yeah.
All right, so this is how this is the beauty of what we've just found out, okay? This problem, starting over from scratch, says that what I can do is I can just plug in the values that I have. Sine of x plus 2. And then I need the derivative of this function. What's the derivative of sine x? Cosine x.
Okay.
And that's it. I don't have to do any of the antiderivative derivatives. I didn't actually do, truly, very much calculus at all, did I? Whoops, I just was going to distribute the cosine.
No matter what the bottom number is?
Yeah, the bottom number doesn't end up mattering because when you do your limits of integration, it ends up subtracting it off regardless. Because, and I know I just erased it, but what you saw is you saw that when it was 0, it went away. But what would have happened if we'd taken a derivative of something that wasn't 0 at the end?
No, that's right.
It's a constant at the end regardless, right? And the derivative of a constant is 0. So the constant number at the bottom makes no difference.
The integral would have been different, but
Yes,
it wouldn't have changed your answer because your answer is the derivative.
correct. Because when you do the derivative after that, then you end up deleting it out. Yeah.
If you have like 2x on the bottom.
Well, we're going to do an example where we've got an x on the bottom and on the top. Okay? This one has a lot in it. Okay? So the first thing that you have to understand is the fundamental calculus, the second fundamental calculus theorem is hinging upon having one of those values, either the top or the bottom, but it's written in terms of the bottom, having a constant there. And this one doesn't, right? But let's see what we can do about that. So the first thing we're going to do is we're going to separate this into 2 integrals. And there needs to be a number, and I'm going to choose the number 0, but you can choose whatever you'd like, because it really doesn't matter. Do you remember in our last section, we had a theorem that said we could do this? Do you remember that? It said you can separate it. I drew a number line and I told you we can go from here to here and then from here to here, remember? I can separate it into 2 different integrals.
And then you can flip it.
And then we can flip it. That's my next step. Okay, so the fundamental theorem needs the constant on the bottom. Well, my first integral here has the constant 0 on the top. Agreed?
Yes.
So I'm going to flip it upside down. And then I actually told you in the last section, too, that we would have a use for this fact of being able to flip it. There's our use. I love it when one day, you get all those pieces together and I keep telling you, see, I told you so. That's what happened right there. See? Told you it would be useful. 2 pieces of usefulness all in one day. Hold your horses. Okay, here's the cool thing. Aside from the negative here at the front, this is exactly Fundamental Theorem of Calculus because it's got just plain old x on top. Which means I can take this and I can replace the t for x. So this is x squared plus 4. If you want to think then I need to do the derivative of x, so be it. The derivative of x is 1 and you can write it down. If it helps you to remember always I'm going to take the derivative, then do that. Write down the 1. Won't hurt anything. The second piece, I'm going to do the replacement again. So I'm going to have 3 minus x squared plus 4. And then I need to do the derivative of 3 minus x, which is negative 1. So we do have to make sure that we get it on that one. And now let's just clean up of algebra, okay? So let's clean up the algebra and we will be done for today. So this is negative x squared minus 4 plus, over here I have 9 minus 6x plus x squared plus 4. All of that will be distributing through with a negative 1. So I have minus 9 plus 6x minus x squared and minus 4. And let's collect some like terms. So what do I have?
Minus 9 plus 6.
Let me start with my x squareds. Negative 2x squared. What would be the variable for the constant, or the linear term?
What'd you say?
The next piece, descending order of exponents, what's next?
Oh, the 6x.
The 6x. And then what do I have for my constants? Negative 17. All right, and we will stop there for today.